Good morning, everyone, and welcome to the 23rd ETP4HPC webinar. I'm Pascal. I'm ETP4HPC's Communication Manager. My colleague Mike is also here to help run the show, and you can see all the speakers and panelists. I will introduce them a bit later. But first of all, for those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation in high-performance computing in HPC. And we are a private member of the Euro HPC JU, which is the organization in the European Commission that addresses HPC. And our role is to propose research priorities for Europe in the area of HPC. And that's, well, exactly what we're going to talk about, those research priorities that we identified. So today we are going to present two topics that are taken from our SRA5, our strategic research agenda, and they are programming environment and mathematical methods and algorithms. Before we start, I would like to share one information with you. It's about the ETP4HPC conference. It's the first time we organize a conference open to all. It's going to happen on the 8th of March, just before our General Assembly near Amsterdam. So you're very welcome to join us for a day of exchange and networking with our members. The conference will include keynotes by European Commission representatives, by representatives of the Euro HPC JU, also a representative of Destination Earth. We'll have two BOF that were proposed by our members. We'll have an info afternoon dedicated to project opportunities and IDs, and a networking dinner. I mean, if your organization is a member of ETP4HPC, you're very welcome to attend both the conference and the General Assembly, even if you're not our main contact person. If your organization is not a member of ETP4HPC, you can attend the conference on the 8th of March. So the link is in the presentation. I will maybe put it later in the chat so you have it. So that was it. Let's get back to our webinar. So very quickly, practical information. The webinar is recorded. You will receive the link tomorrow. The webinar is in listen-only mode, but you can ask questions in the question panel. You can also download handouts. So the slides are one handout you can download today directly here. And you can also download the SRA if you don't have it yet. It's here among the handouts. So now I would like to introduce our speakers. So we have two speakers today. Paul Carpenter from BSc. He will handle the first part of the presentation today. And then Utz-Uwe Haus from HPE. He will handle the second part. And as our SRA is really teamwork, we will also welcome several panelists. First of all, Michael, actually I can't see him, but he should be here. Michael Mounts, he's our SRA leader at ETP4HPC, so he's not presenting today, but he will be here for the Q&A. Dirk Pleiter from KTH will be here also for the Q&A. And we also have Gabriel Antoniu from INRIA and Guy Lonsdale. So we feel it's really important to involve several co-authors of this SRA, not just the presenter. So very quickly, that's the agenda. So we will start with programming environment by Paul, and then we will go on to mathematical methods and algorithms by Utz-Uwe. And we'll keep all questions for the end. We'll have a Q&A session at the end. So, Paul, I will hand over to you. Yes, you should be able to share your slides.
Okay, thank you for the introduction. I'm just waiting to share the slides. Hang on, I probably need to click somewhere. I didn't get, here we are, sorry.
Yeah, sometimes there is a slight delay.
Do you see the right screen?
No, we see the presenter, not the slideshow. Yeah, that's perfect.
I think it should be
Thank
okay
you.
now. Okay,
Yes,
so
thank you.
Thank you for the introduction, Pascal. Good morning. I'm Paul Carpenter, and I'm going to present the programming environment. I'd like to thank my co-leads, Professor Gabriel, Antoniu, and Guy Lonsdale, who are also on the call, as well as the rest of the SRA programming environment team that helped write the chapter. So, hang on, we have a problem here. We've missed a slide. Very sorry about this, but let me try again. Somehow it deleted a slide. Yes, we are okay now. Okay, so we identified 4 main trends in the programming environment. Some of these are not actually so new, but they're still important. So I'll go through them in the first slide. So the first is it's very important to remember that HPC applications are very complex. They embody a lot of domain knowledge about the problem to be solved, and they have very long lifetimes measured in decades. And it's not reasonable to expect the application developers to bet the farm, as it were, on an experimental new programming environment. At the same time, we have a very vibrant research ecosystem of programming model research in Europe, developing lots of very good programming models. The thing is that the most successful of these, if we want them to be actually used in production, which I think is the point of this, requires some kind of formal or de facto standardization, so that the application developers can be confident that the programming environment will be available on all the machines that they're using, that the support that they have is high performance and stable, that it's supported by the vendors. So in fact, if there's an issue, they can call up the vendor even and be sure that it's going to be well supported. Another trend that's very important is what we call interoperability. And in this sense, we're talking about the basically the gap between the source code written by the application developer and the machine execution. So as the programming environment becomes more complex, the machine itself, the hardware, and also the software environment becomes more complex, this gap can become larger. And just to make this concrete, just to give some simple examples of when this goes wrong. This, for example, if a user of a C++ template makes some error, there's pages of errors that in code that the application developer doesn't know, or maybe giving wrong parameters to runtime gives a seg fault in some routine that, again, you don't know. But it's not about these specific examples. It's a general concept that whatever abstractions are used by the programmer should be seen through the whole tool flow. Maybe in the performance analysis, if you're working in terms of tasks, you want performance analysis and debugging in terms of tasks. I think this is an important aspect. Another one is we see more workflows that combine traditional kind of HPC numerical simulation with data analytics and AI. And this gives maybe better results in some cases, or higher efficiency for existing use cases. It may also enable new use cases, for instance, autonomous driving, digital twins, and so on. But in many cases, this means integrating different programming models for the different domains or different kinds of systems, which abstract away details of the hardware, maybe in different ways. And the key word here, which actually doesn't appear on the slide, is composability. So some way to compose these different programming models with defined rules in a way that makes sense. And then finally, we have sort of dreaded word, co-design, which is essentially, it's when you're handling scalability or efficiency, which is needed for exascale if you're thinking HPC, but also across the whole digital continuum. These kind of non-functional considerations, energy efficiency, scalability, maybe even resiliency or whatever, require coordination across the whole of the stack, from the application, program environment, system software, I/O, storage, system architecture, system components, and this, as a kind of central part of this, the programming environment is part of this co-design. Now, going through some of these aspects, maybe in a little bit more detail, we have higher productivity programming. So actually, this first statement here, a HPC application development is still tedious, error-prone, and not portable. This statement, we made essentially the same statement in slightly different words, not that different, in the first SRA in 2013, and it's still true, right? But then one very basic question is, if these programming environments are in some sense improving the productivity, dealing with the tedium and the error, the possibility of making errors, removing the need to kind of redo things with different architectures, how do you measure the programmer productivity? We need some way to quantify it, because we want to be able to compare different approaches and make progress in the field. And actually, one thing that came up in the SRA discussions was that there are no clear metrics that work for HPC, where the interest is you're not writing new code, you're maybe porting it, or you're making code that is portable, that's going to have benefits in the future. How do you measure this? So this is something that is important. An important thing, of course, or approach in dealing with this is to separate the algorithmic concerns, what you're going to do, and which would be in a maybe architecture neutral way, from the implementation, how you're going to do it on a particular architecture. Clearly, this is a nice way to support diverse systems. Maybe also the people involved or the experts in the different aspects of this can then, work on separate parts of the problem. This is important. It still needs to be done in a way that supports existing codes. And approaches for this kind of thing may be meta-programming, maybe adopting high-level languages or scripting languages like Python or Julia, directives, libraries, possibly DSLs. So we got this. Then support for the specific hardware. I mentioned the diversity of hardware. It's not just the hardware, it's also the system software that comes with it that maybe has its own quirks and features that have to be dealt with and presented in a uniform way to the user. Different kinds of compute, different kinds of memory, maybe acceleration in the network. And the layer presented to the application should, if possible, be vendor neutral and transparent to abstract this heterogeneity. So a key issue is we want to put more intelligence in the runtime, and we need to decide what kind of information is collected and how from the programmer, maybe as directives or so on, and what is transferred among the different software layers to enable this optimization. Giving information about different ways of laying out the data, data movement, dynamic load balancing, maybe resiliency. Malleability I mentioned more in the next slide, but just to say briefly, this is the ability for an application to adapt to or maybe change or request changing resources, maybe a new node, or to release a node because of its own application needs or the system availability. And this, well, I'll say in the next slide, but this is something that is very immature at the HPC side. But anyway, this is just one of the aspects. For this, the intention is more declarative information. So we're talking about transferring information and the programmer giving declarative information rather than the micromanaging what to happen. There's this issue of trust. The application developers need to trust the lower levels of the stack to do the right thing. Of course, that trust has to be earned through the high performance and the stability and the so on that I mentioned before. And then as a final note related to this, runtime intelligence, I think it came up that, you know, there's more scope to use machine learning techniques in runtime, maybe in the compiler as well. So this is the topic that I mentioned about malleability or dynamic resource availability. So there are situations where the application has to react to certain events. So maybe it's on-demand simulations, maybe there are real-time constraints. So this is, in a sense, changes in the data or the problem presented to the application. Or it could be the resource availability, so the other applications in the system maybe have to make way, or maybe some spare resources have become available that can be given to a running application. But I think we probably all know HPC applications typically have static resource allocations. So you use your job manager, you get a certain number of nodes for a certain maximum amount of time, and then you run an MPI program which does the domain decomposition and uses those resources. In fact, MPI has supported dynamic process management since 1998. So this is, I guess, 25 years, but it's difficult to use, it's poorly supported, and very few applications make use of this MPI ComSpawn capability. So there's ongoing work actually in some of the Euro HPC projects. I'm aware of DeepSea, Admire, Timex. There's a workshop, the first workshop I see that last year, and there's another one this year to work on through the whole system software and programming environments and applications, of course, the support for what I guess is similar to elasticity in cloud computing. As far as the programming environment is concerned, the data redistribution, so finding ways to simplify this and help the application optimize the data redistribution, this is a way that the programming environment can really help. Next topic, interoperability, composability, and standardization. I mentioned most of this, actually. So the challenge, support complex workflows, combining simulation, analytic learning across the digital continuum. We have different frameworks for HPC, for cloud, for edge. We have different machine learning frameworks and HPC libraries and so on. We have this issue with interoperability, which is even harder when you're combining multiple programming models. The composability on the compute side, also unified APIs for data, maybe combining the big data processing, batch and stream, with in situ and in transit HPC data, and different kinds of data access, byte level, object level, and so on. And as I said at the beginning, standardization, if we want to do something that's really used, and the point is that we are trying to help the applications run on the real machines, the production use has to be the goal. In some cases, for some research, it's quite a long-term goal, but it has to be the goal. And really, standardization is seen as a crucial way to get this take up. So next topic is performance analytics, debugging, and program correctness. So these are always important. The title on the slide is wrong, actually. It should say program correctness. So one issue is these tools at large scale collect a lot of data. How do you manage that? Is there some kind of sampling or recognition of patterns or so on to reduce this? The goal is insight, so some kind of intelligent analysis. As a user, it's very tempting to guess the problem and jump to a solution, but often the underlying problem is maybe not what you expect. So it's this intelligent analysis is very important. Understanding the right abstractions, relating the data access and transfers to the program itself. So Data transfers, for instance, are not visible in the program source. Well, for the memory hierarchy, they're generally not. Across nodes, depends what you're using. Some higher level models or libraries, again, it might not be very clear in the data source, in the program source. And then proving program correctness. There's really not very much of this I'm aware of in HPC that includes the parallel and distributed execution. So that runs through most of the topics in programming environment. I wanted to talk a bit about the interaction with the research clusters. So in the development of the SRA, we have the working groups on the right-hand side, which are essentially the stacks. The different layers of the hardware or software stacks, programming environment is there. And then the research clusters are more vertical aspects. And I wanted to draw attention to the interactions between the programming environment and sustainability and the heterogeneous HPC. Although, of course, I made some reference to interactions with the HPC and the digital continuum, and also the urgent decision making, which would relate to the malleability topic. So related to sustainability, what is sustainability in the concept of HPC? It's things like energy efficiency, so gigaflops per watt. It's the total cost of ownership of the HPC systems and so on, and the environmental cost. So the programming environment helps pretty directly through enabling high performance. So it's going to reduce the energy consumption, also reduce, if you've got a fixed problem and you know what you need to do, it reduces the size of the system that you will need to do that. Easier to use programming paradigms reduces the effort to create and maintain applications, which is a cost, right? And then the stable programming environments further reduces the effort in maintaining the applications, and it allows longer term use of older machines, maybe that don't have the latest programming environments, but still have the ones that are being used with newer applications. And then on the heterogeneous HPC computing, or HPC, I already mentioned the different components of HPC becoming more heterogeneous, and the workloads as well, and this making programming systems more complex. So essentially the programming environment helps to a great deal here, because the tools, and by the tools I mean the whole programming environment, have to be adapted for the heterogeneous systems. So my last slide actually is a quick mention of a white paper that was released by ETP4HPC in 2021, October 2021, highlighting the benefits of task-based programming in terms of performance, portability, and HPC. So tasks are already mainstream in HPC. They're well supported by OpenMP. They first appeared in research in 1990s, so they're hardly new. So read the white paper. It gives maybe also some background on this difficult, time-consuming, and so on, and the need for performance portability, and it explains why tasks give a open, clean, stable interface that allows the problem to be expressed in fundamental terms. By not being specific about the resources, we get some benefits in terms of maintainability and malleability. And again, this comment about the most successful approaches should be standardized. And that's it from my presentation. So I hope it's been interesting, maybe informative. As Pascal said at the beginning, take note of any questions, and we'll answer them in the end. We also have Gabriel and Guy on the line for the aspects I'm not so strong on. And I'll hand back to Pascal to introduce the next speaker.
Thank you. So I will put the link to the white paper you just mentioned. I will put it in the chat. And so thank you very much, Paul. So we will do send your questions, but we will answer them all at the end. So Utz-Uwe, ready? I will hand over to you.
Let me go off mute.
Did you get the prompt to share your presentation? Oh, have we lost
I hope to be
Utz-Uwe?
back. At the moment when you try to hand over, WebEx froze. Can you hear me?
Yes, 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 yes.
So let's hope
Okay, so I will invite you again. Okay, hope it works this time. No,
it's frozen for me.
it's frozen for you. We have you twice in the list. That's very curious.
So something is coming up. So maybe it's just slow. Can you see my slides?
Yeah, yes, we can see your slide.
So I'll go
And
off
it's
the
even in
webcam.
slideshow mode.
Okay, so I'll shut off my webcam just in case this is a bandwidth issue, which I hope it is not. You've all seen me and can see me in the panel. So thanks a lot for organizing this. Ready to, with 2 minutes delay, get started on the second installment of this webinar. This is on the mathematical methods and algorithms part, and I'm presenting, of course, not my work, but the work of the entire working group, which I listed here. Dirk is on the panel today, and some of the other ones are in the audience, I saw. So I'm looking forward to a fruitful discussion in the panel afterwards. So this is the SRA5 working group, Math and Algorithms. And of course, we welcome new members if you're interested in the topics that we touched upon here. I've made an effort to basically guide you through the long text that we wrote. So if you see something on the slide that I'm not talking about, it's all in the text. Maybe this is a way to get started on the reading if you have missed things, or get you interested in the document. We start with research trends and current state of the art, a list of challenges we identified for the coming 3 to 4 years. And then I want to discuss the intersection with the sustainability cluster, which is a topic I'm very much interested in myself at this time, but we've seen in the chart of Paul that all our different research areas really touch into sustainability these days, which is good. So research trends and current state of the art. The first item is we see the evolution of hardware features impacting the efficiency of our existing methods and algorithms. This is due to the GPU and also CPU trend offering more lower precision arithmetic and tensor operations, which is both an offering but also a challenge, because utilizing those really requires mixed precision algorithms, and that those are not mainstream in what we usually turn to thinking about a problem for the first time. We also have more and more complex memory hierarchies. That's been a trend for multiple years, and we've predicted that previously, but it's really a reality now. And so data locality aware algorithms, active data placement choices as part of the algorithms developed become a real trend. We heard a bit of that mentioned by Paul on the other side, on the technology side, but taking it into account in the algorithms like we did with out-of-core computing in the 80s and 90s is really coming back. The second one is we need to focus on performance gains above the CMOS level. We all know that the CMOS level is not offering the improvements year after year that we've seen in the last decades. And that really means hardware, software, and algorithms layer all need to work together on the energy efficiency that we're striving for, and also harvest the CMOS efficiency gains that have gone underutilized because we could rely on the hardware improving and not improving algorithms all the time due to the boost below. There's also a trend to look at time to solution versus energy to solution as two very different metrics, where the latter one is really the one that allows you to operate a large system, an exascale system, reasonably efficiently. If everybody wants time to solution, and in a workflow that's maybe not even the part you really care about, then the whole system will not be efficient. And the third one is really unconventional architectures challenging the methods side. So a data flow architecture requires numerical libraries still, and we have kind of ignored them as special purpose in many ways. Or come from the other side, have an algorithm that needs a certain architecture and be fine with it, but not looked at the portability of that. Devices are also becoming less reliable, either individually because of the silicon process becoming more and more fine granular, but also really the question of if you have 1 million devices of the same type, some will fail all the time. So algorithms need to be robust. They need to take that into account as a feature of the system and not always assume it's an ideal Turing machine. Going along with all of these is in-memory or in-network compute, a topic that's been discussed academically a long time, but really coming to fruit with hardware being available for that in recent years, which makes an extra requirement of algorithms to be truly distributed. And I don't mean to downgrade MPI distributed or task-based distributed work as such. That is a valid way of approaching distributed algorithms. But if you have different computing devices that are so different that some of them are really tiny and only specialized functions can be executed, even on task-based programming environments, that's an extra annotation that you need to take into account for certain tasks to be only executable on certain devices. And system topology plays against you typically. So the algorithm side needs to take that into their repertoire of execution units and really change the way we build the algorithm from scratch. Challenges that we see. And all of these will allude to some of the trends we saw before, but in different ways. The first one really we think is robust methods and algorithms that enable the extreme scalability. I've talked about that before. It's instruction level to system size, parallelism that we see, and we believe parallel in time integration and hybrid stochastic and deterministic algorithms will play a big role in utilizing these features. The second one is that algorithm cost starts to be or is being dominated by the cost of data transport. And if you remember your computer science 101 view of algorithm execution, time, cost, accounting, then movement is just a constant factor of instruction execution time. But in practice, it's a very, very large factor. It's not exponential, but it's really a large factor or a large polynomial of the execution cost. And so our evaluation of the efficiency of algorithms needs to change, taking that into account explicitly. Both when we move between different levels of the memory hierarchy, but also if we move at system level and through the network and to storage. That requires better understanding of lower bounds of the transport required so that we can make reasonable judgment on the efficiency that can be achieved by a given implementation. And asynchronous algorithms will of course help. We've spent a lot of time in the community in overlapping compute and IO, but that was focused on disk IO or tape IO if you want. We need that kind of effort at different levels. And the third one is really robustness against failure. Failures need to be expected, can be silent, can be explicit. Explicit errors are usually easy to deal with, if only by a board, but silent errors are harder, and we do see them at scale. So we need fault tolerance at the algorithmic level, say your numerical algorithm being able to deal with numerical outliers that appear due to silent errors. research in error detecting, error aware and error oblivious algorithms as such is warranted because of that. And again, mixed precision algorithms may help here a lot. The second topic we identified is algorithms that relate to machine learning. We see data-driven algorithms as new opportunities for HPC and really no separation between AI, machine learning, deep learning, whatever you want, and HPC. These are just very challenging compute problems for the HPC community. But there's also the option of combining them, combining these techniques with more traditional workflows. We even saw that in the programming environment talk of Paul just now. They fall ideally into the class of surrogate models that we know from first principle models, where you have surrogate models to simplify at the right level. Physics-informed neural networks may play a role here, where you couple some of the abstract and hard to understand neural network behaviors with physical information that makes sure your solutions represent physical quantities and systems. There's an issue here that complex or chaotic systems like multi-scale, multi-physics problems in weather and climate still need a lot of work in the machine learning community. It's easy to say, yes, we'll just apply a deep learning technique and not realize that these are smooth solutions, convex solutions at their core, even if the problems are non-convex. So there's training instabilities. There's the question of how do you find a neural network architecture in the first place? Can that be automated? And there's fundamental mathematical limitations that need to be understood to not run into fallacies. And the third one is that algorithms based on machine learning have a lot of parameters, and so they need help in selecting these parameters, and that's a computational problem. So you can bootstrap machine learning on top of machine learning or other optimization algorithms to identify these parameter choices that are good to either improve the quality of the solution, the time to solution, energy to solution, same metrics that we usually look at. We need approximation guarantees for such choices because otherwise it's just a large set of unproven heuristics. There may be instance-specific specializations that allow us to speed up the process. And there's the whole topic of hyperparameter optimization in an abstract setting. The third topic we really find important is system resource management and co-scheduling. I've mentioned that in the intro because we have so many different and differently abled components in our system, the scheduling problem becomes harder. So with workflows models as directed acyclic graphs and declaratively, hopefully, we can better judge what should be run when and where and what it depends on, maybe also track the data movement. And there have been good progress made in that in different Horizon calls Fed HPC projects. But we still need workflow-aware scheduling policies implemented in actual resource managers. These involve complex optimization problems. Some of that needs help from the operating system and the rest of the software stack. Some of it can be in your programming environment or some layer in between. And there's very many policies conceivable, even on the same site. So it's not so much a site decision or a community decision, because objectives may vary. We may have balanced utilization of the system so that all racks run at the same temperature, or all devices are exercised at the same level if you know that failure rates increase with utilization. There's energy consumption that can be saving energy. It can also be guaranteeing a certain level of constant consumption because you're maybe recycling the hot water from your system to heat a community nearby, and you have service contracts on minimum water outlet temperature. So these are opposites in the same problem of optimization. There's time to solution, data movement, resource utilization. But there's other policies on interactions with the resource managers. How granular do you want the system resource manager to work? Can you achieve co-scheduling of different components of the same workflow, different users, jobs, because one may utilize an accelerator set more than the other, but not utilize the other components? and what is the queue time that you can guarantee or have to ensure. And the problem has stochastic components because not every run is like the other. The deeper memory storage hierarchy influence the resource management requirements. We need algorithms for data-aware scheduling, data placement, and in many cases, we're lacking the information from the application side and the programming environment. So that's a link again to Paul's talk before. And the large-scale scheduling problem runs into a very distributed nature of computation, which is across federated HPC systems. And we have a whole white paper on federation from the ETP SRA team. How do you federate storage? How do you deal with the latencies and bandwidth constraints on that? Both in an HPC to cloud and edge, digital continuum, but also if you move parts of your workflow between different, say, Euro HPC systems as Destination Earth is planning to do. Maybe there's no central coordination and there's a data consistency issue that may require more work on consensus-based algorithms. And speeding up towards the end, there's great opportunities for a co-design of algorithms and system architectures because systems are no longer uniform off-the-shelf boxes of this or that type where you decide what you buy and then you have it. Maybe you have a choice at the system level, but not inside. We have different memory types. They contribute significantly to the system cost. So choosing how many components of which type depends on what your algorithm allows you to utilize, which capacity you need in which tier in the memory system. And that's a co-design problem. An interesting one. The goal of reducing energy costs really ties into matching hardware and software capabilities. Communication avoiding algorithms are an interesting topic we see here. Reduced precision algorithms, again, I think they show up for the third time here. And utilizing specialized instructions. So if you think of the RISC-V ecosystem, where it's reasonably easy to customize your instruction set, there will be room for utilizing that if your algorithm really requires it. And you can make use of it. So trusted HPC computation is the third part. That's a topic, again, I'm very interested in. How can we achieve system utilization improvements because of sharing a system better, even across untrusted partners? In the HPC community, we usually trust our neighbors on the same system. And that's not true in the cloud setting, and it's not true in a well-utilized, compartmentalized system, which is dynamically reconfigured in HPC, and that's what we see coming forward. And so encryption needs to be integrated into the full software stack. We may even talk about homomorphic encryption, and I see some of you really probably being very wary of that if you talk high-performance computation at the same time. But it's a relevant topic for the algorithms and math programming environment community here. All of that ties in with vertical integration. So how can we make these heterogeneous applications portable at the algorithms layers, at the compilers layers, at the middleware and software layers, and at the hardware layer? We want to be able to move all these new technologies from one side to the other, from one generation of hardware to the other. And so that drives us towards using higher level representations, again, tying into the programming environment questions. Finally, I'm going to close with the intersection with a sustainability research cluster. I think some of my comments will already have made you aware that there's a strong tie-in here. But we want to separate two aspects. One is the operational aspect, which is the one that we all think of, better utilization, energy consumption reduction. How many watts and how much carbon dioxide do you want to spend to save a few tons of carbon dioxide in a process? Right? If you optimize an industrial process using HPC, you better make a savings out of your solution that's bigger than what your HPC system consumed during the computations. And the resource life cycle of your components plays a role. Can we utilize components longer? Can we repurpose them after the initial super high performance aspect usage in different parts of our systems without putting them into recycling just yet. But there's also HPC integration into a circular economy as a facility, as a tool. So integrating the systems with the grid, integrating them as tools for dynamic optimization of processes and systems that should work at their optimum efficiency in order to be sustainable economically and environmentally. And so that's why we singled out 5 of such topics where algorithms for sustainability can play a role. One is the classic HPC approach, development of new or improved technologies. In particular, we think wind turbines with computational fluid dynamics around it have shown first successes, but will need more work. The long run times, even on exascale class devices, is still a challenge. The fault tolerance will play a role. And digital twins in general are coming up at all levels for all kinds of industrial and socioeconomic systems. There's the reduction of the impact of HPC usage at all levels. I talked about that enough. The energy consumed by components may be improperly utilized. So that's the scheduling aspect, where we can shut off systems parts if they're not utilized and quickly turn them back on. We don't really have the technology in our software stack at this point. We also don't have the algorithms to decide that in a robust fashion to avoid that we're only turning stuff on and off all the time without really having guidance on why. And tying this into a site-aware, grid-aware operations schedule. Then HPC is part of the regular IT industry, so the R's of sustainability is repurposing, refurbishing, and remanufacturing play a role. And finally, data centers should become active grid participants. And you may say, well, that's not an algorithmic problem, but trust me, if you build a model of the AC or DC grid, that's a very interesting mathematical model. It's a very hard to solve problem. Which units should be committed for which time in your schedule according to weather or climate information, according to robustness and ramp up, ramp down effects in the network to have stability. And so if data centers come on, they can play the part of a very smart consumer and very smart energy source. And we can discuss more about that in the panel if you have further questions. And with that, I thank you for your attention. Ready to answer questions and Mike,
thank you, Utz-Uwe.
Trying to find my window here.
Okay, so thank you very much. So yeah, we have questions already, so I think we'll start right away with the questions. Are you ready, dear panelists? So the first question, the questions are in the chat. I'm copying all the questions in the chat. So this is for all attendees and for the panelists. Look at the chat and you will see the questions. So we have a first question. It's for Paul, but maybe Gabriel or Guy will want to answer it. So I will read the question out. Are containerization solutions like Docker, Podman, or package manager like Gix specifically made for reproducibility used in HPC environments? They could make it easy to instantiate reproducible and consistent programming environment. So this is a question from Bruno Andre Rodriguez Stello. Sorry for.
So I could give a
so
first.
Who takes the question?
Do you hear me?
Yes.
Okay, well, I'll give a first answer and then the others can maybe add to it. So containerization, I do see a lot of interest. I must say, when I'm looking at the actual practice, at least from my side, it seems very immature, or at least not used a great deal actually in practice. Although there's Singularity, which is now called Aptainer, is a containerization solution made specifically for HPC. On the package manager, I've also seen, so there's Easy Build and SPAC, are two package managers developed specifically for HPC that, for instance, they deal with having multiple versions of a compiler, so GCC and Intel maybe, and different MPI libraries and so on. And I have seen an interest in the projects I've been involved in to adopt and to support both of these for the reason that you give, basically reproducibility in terms of having a reproducible installation. I'll hand over to Gabriel or Guy if they maybe have more to add.
Yes, Gabriel or Guy, anything to add to this?
Nothing to add.
Yeah, well, I agree with Paul. So it's emerging. It's maybe not so mature, but well, at least on my side, I can witness a number of efforts in that direction. So there is definitely interest in that. There are definitely efforts in that. I confirm for Docker, Singularity, and Spark, for instance. I'm aware of existing efforts in that direction. So I think there is a way. It is a way to go.
Okay. Thank you. So there was a second part to Bruno's question. So is the functional programming paradigm something that is also more and more used by researchers, as this paradigm makes it easy to execute code in parallel? So Paul, Gabriel, Guy?
I can give a first response to this, which is I spoke at the end about task-based programming models. And at least in OpenMP now, these tasks can have dependencies defining the inputs and outputs of the tasks. So the runtime, at least the runtime I'm working with, takes these dependencies, builds a DAG. So in some sense, it's very similar to what I understand goes on with functional programming in other domains. I think maybe we have some things to learn in terms of lazy evaluation. But that's the connection I see with HPC and functional programming. Maybe again I'm missing, so the others can comment.
So Guy here, a historical note. Many moons ago, I was involved in a German supercomputer project called Suprinum, and there were some activities there to do functional programming in what was then an HPC context. I think they were using Prolog. And a couple of years later, there were some EC projects looking at using such in HPC, but I don't think there was any real positive impact of those. And I don't recall seeing anything since then. So that sort of went down like a lead balloon. But maybe we still have things to learn from them. Who knows? Things change.
Okay, thank you. So now we have a question for Utz-Uwe and maybe Dirk. So it's a long question, so I really encourage you to look at it in the chat. So question from Martin Trust. Do you consider parallel in-time algorithms to trade the energy to solution for time to solution thanks to better parallelization? Or in other words, do the parallel in-time algorithms require a higher number of floating point operations to solution compared to traditional sequential in-time algorithms, and hence entail higher energy to solution cost by construction? How does it go together with the energy consumption aspect?
Yeah, I mean, first of all, the goal of these parallel time algorithms is to reduce time to solution, but by using more hardware and then, of course, also doing, say, a few more operations. I'm not sure, and I'm not aware from the literature that there has been, say, an investigation in terms of how energy to solution and time to solution compares here. But given that the additional amount of operations which are being performed in these kind of parallel time algorithms is not that significantly larger, and it's not just the execution of individual, say, instructions which is, say, causing the energy consumption. I suspect that overall the impact on energy to solution is rather moderate. So I mean, you basically reduce, in the ideal case, the time to solution, but you increase also the amount of hardware which you put in place, and then how that the trade-off is that of course also depends very much on the given hardware architecture. I mean, how much base power consumption you have, and that may of course then also play against the reduction of the energy efficiency. But my suspicion is that, like in many other applications in HPC, we often have a very strong correlation between energy to solution as well as time to solution.
And I think we're seeing a lot of cases where the compute units are underutilized in favor of data movement. So a few extra operations may not cost that much because there is a base energy consumption that's just unavoidable unless you turn down frequency, but then your time to solution will also go up. So it's really something to be investigated, I guess. And remember, the presentation here and the SRA statements are not about this is how things are. It's this is what we should work on in the next 3 years. So if you like that topic and you think this is a good thing to go ahead, we're not saying do it like this. We're saying this is where we see the biggest opportunities and challenges. So maybe that's an investigation worth doing.
That's for the next SRA.
Yeah, and it even starts with some phenomenology, right, in terms of also having certain knowledge about what is the energy footprint of given algorithms. And I think that's where we still, I mean, there have been, say, investigations in this direction, but they are still rather few.
Maybe I could just comment that there's a project called TimeX amongst the Euro HPC 19 projects. I'm not involved in it. I don't know really anything about it, but I'm aware that there's an ongoing project that's specifically looking at parallel in time algorithms.
Thank you. Anything to add, or can we go to the next question? No? Okay. So another question to Utz-Uwe as well. It's a question from Manolis Maratzakis. Hello, Manolis. Can you elaborate on side-wide energy-aware operations? I can see this to be feasible. Yes. Okay.
So,
do I need to read the end of the question, or off you go?
I'll read it as I go. So clearly for a manufacturing facility, this is the industrial side of things, right? But let's think about an HPC center as an industrial center. You have cooling facilities of different types. Let's say you have some chillers, you have some real cooling devices that take more energy. You have an outside atmosphere, which for some centers last summer was awfully warm, more than designed. And then you have different aisles. You have different types of equipment, fully water-cooled, partially water-cooled, air-cooled. And you have possibly, many centers are associated with big research infrastructures, site-wide interactions with other research equipment, like fridges from the biosciences or particle systems for physics experiments. So if you take into account that your data center is both a consumer of energy and a producer of energy in terms of warm water, you can tie it in like any other large equipment in an industrial setting. And if you go a step further and are ready to use your USVs also to provide power back to the system or to your local site distribution system, if you're confident, right, that your USV can be run down to 50%, maybe you can also be a provider of energy. Maybe in the future we'll also have fuel cells or something on site that can be powered if we can't utilize the power, but as a consumer on the grid, have been asked by our utilities operator to consume more for this particular hour, but we don't have the jobs. So if you tune your schedule in your HPC system to be compliant with the current cooling cost at this time of day, or utilization of other equipment nearby over the weekend or week, day, night schedule, heating requirements for classrooms versus dormitories on a campus, it's really one component of a big system. And inside, some aisles may run a few degrees warmer and you don't care because they have air to dissipate, while the fully water-cooled ones have a very tightly controlled temperature that you can't deviate from. Maybe you can deviate from it if you switch off half of your GPUs. So this is really a large-scale to small-scale integration effort, where I really think we have great opportunities to understand our system better. And just on the very practical side, talk to your favorite site where you know people well. How often the people who look at the very big cables coming into the building and the meters and the power stability talk to the ones that measure CDU level currents on the system side. Typically, it's different people, it's different schedules, it's different operating consoles. And only on rare occasions, if things go really haywire, do they talk to each other about, could you maybe do a bit here so that I don't have a problem over there? And we would really have the building infrastructure management system integrated with the system control part of it, if only for monitoring for a start. And then the actions can come later. That's what I wanted to express here. And then if you have that, that's a highly interesting scheduling problem as an algorithmic problem.
Good, thank you. I don't see any other question coming in for the moment, but we have reached the end of the webinar normally. So do you have anything to add, any of the panelists? Oh, here is another question. Let me time. Okay, question from Sabri Plana. I'm putting it in the chat. Do you consider that Intel One API programming model will help to address some of the challenges addressed by speakers today? Who can take that one? And I think we'll close after that one. No?
So an uninformed comment then, Guy here. I have spoken to the Intel people, and my understanding is that they're actually bringing things together that exist up to now. So a one API. So things that are there, supporting different current programming models are brought together in their one API interface. But looking at what we were talking about, we were looking for the strategic research from now on. What would we need to be done beyond the current versions? And that would be my take on that. But it's slightly ill-informed because I don't program myself.
So I'll make another medium-informed comment on that. I think you're right, Guy, in that there's lots of useful things under this umbrella of one API, like bringing tasking to people who've ignored it before, right? And strange additions to C++ that may or may not turn out to be very useful, but they're out there. And so, yes, there is an opportunity, like in any environment that people have in their hands. And so, yes, there is an opportunity to address some challenges, but it's not because of one API as such, just because of the market reach, bringing the things that we should have been using over the last years to new people. For the challenges in implementing new ideas and developing new ideas, it's just a start.
Thank you. So I think this will be the last question. Has any of our panelists maybe something to add or no? Okay, well, thank you very much for being with us today. Thank you for your time. Thank you, Paul, Utz-Uwe, Gabriel, Guy, and Dirk. Really, we appreciate. Thank you to all our attendees. There will be no webinar in March as there is the ETP4HPC conference and also the Euro HPC summit. So it will be a busy month for us all. But we'll be back in April with a new topic. We don't know what yet, but we'll let you know. And you will receive the link to the recording of this webinar tomorrow, I think. So thank you very much. And yeah, we are almost on time, but we had some technical problems, so okay.
Sorry about that.
Thank you. No, it's not your fault. Thank you, everyone.
Thank you. Bye.
Yes.